Here's video 3 of chapter 6. So we're back to the quantum numbers that we were introducing that are going to describe these orbitals. So what orbitals are, again, is just areas or spaces in the atom where electrons are most likely found. So it's nothing but a space, okay? And it's not a structure, it's just an area or region. So there's several, well, there's going to be 3 numbers that are called quantum numbers that are going to describe the orbital. So the first of the quantum numbers is called the principal quantum number, little n, and it simply tells what energy level the orbital is. So where is it in relation to the nucleus? So n equals 1 is the closest, n equals 2, 3, 4, etc. So that is the principal quantum number. Kind of tells the size of the orbital. The second quantum number is called the azimuthal quantum number, and it's a little cursive L. It looks more like this usually. What it's telling you is the shape of the orbital. So there's 4 different shapes we run into. There's an s orbital, which is spherical, and it's 3-dimensional. There's a p orbital, which looks like a figure 8 or a dumbbell. There are d orbitals that have 4 lobes. They look like 4-leaf clovers. And then there's f orbitals, which we never really draw. They don't all look like this. This is just one example that has 8 different lobes, but they get a little bit more complex in their shape. There are additional orbitals in the atom with different shapes. We just don't go into them here. These are the ones that are occupied by atoms in their lowest energy state. So they're the ones that we are most concerned with. So in this coding, in the quantum numbers, you have codes for these different shapes. If you are an s orbital, your azimuthal number is 0. If you're a p-shape orbital, then your azimuthal is 1. If you're a D shape, your L is 2, and if you're an F shape, then your L is 3. So we just kind of have to memorize, have these really familiar, 0, 1, 2, and 3. The third quantum number is what's called the magnetic quantum number, which is M with a little L. What it's telling you is the orientation of the orbital, okay? So at each energy level, each floor of the building, n equals 1, n equals 2, n equals 3, you have these different shaped areas called S, P, D, and F orbitals, right? Well, additionally to that, you have multiple P orbitals at each floor. You have multiple D orbitals and multiple F orbitals. It's kind of like on each floor of a building, you have multiple classrooms that are identical, just in different areas. You have multiple lab rooms that might be identical, but are in different spaces. That's exactly how this is. So here at each level, you only have one s orbital, however, because it's a sphere. So even if I spin that sphere, it's still covering the same space. So at each level, n equals 1, n equals 2, n equals 3, you only have a single s orbital at each of those. And the s orbital begins at n equals 1, meaning at every energy level, you're going to have an s orbital. The p orbital, which is the dumbbell, the figure 8, there are 3 of these at each energy level. I'll show you a picture in a minute. And they're just oriented differently. Like one is across the x-axis, one's the y-axis, and one's the z-axis. So they're all the same shape and size. They're just covering different spaces in the atom. These p orbitals do not show up until n equals 2, and then they're there from then on. So what that means is at n equals 1, you don't have a p. You only have the s. But at n equals 2, you now have the s and you have the p's. The d orbitals, you have 5 of them at each energy level. They look similar to one another. They're just turned in different regions, in different orientations. And there's 5 of them at every level starting at n equals 3. And then lastly, the f orbitals, there's 7 of them at each energy level, and they begin at n equals 4. So look for these patterns. There's 1 s, 3 p's, 5 d's, and 7 f's at each level. However, they start at different levels. S's begin at n equals 1. At n equals 2, you have s's and p's. At n equals 3, you have s, p, and d. And then at n equals 4, you now have s, p, d, and f. And from then on, you have all of them. Like at n equals 5, once again, you have s, p, d, and f orbitals available. Let's talk a little bit more about each of these. So let's focus on the s's first. Remember everything we know about an s orbital so far. It's spherical. There's only one s orbital at each level, and they begin at n equals 1. So I'm showing you an s orbital at n equals 1. It's just a small sphere. There's also an s at n equals 2. It's a bigger sphere. There would be an s at n equals 3. These are regions. Remember, they may or may not have an electron in them. All they are is just spaces. So we're looking at the magnetic quantum number here, the m little l. So if you are an s orbital, there's only one option for your magnetic quantum number, and that's 0. So start seeing if this coding makes sense. You've got your principal quantum number 2. I've just made this one up as an example. You're at n equals 2. That means you're 2 energy levels away from the nucleus. Your next code is your azimuthal number, which tells you the shape, and a 0 corresponds with an S shape. So what we know so far is that you are an orbital that's at n equals 2. You have a spherical S shape, and then magnetic quantum number just tells you that you are that one S orientation. There's only one option here, which is 0. So we're trying to decode what an orbital looks like using these numbers. If you are a P shape, so this is just an electron density picture. If we took a picture of an atom over and over again, this is where the electrons are found that are in the P orbital. You'll notice they have this dumbbell shape. So everything we know about a P orbital so far. It's a figure 8 shape. There are 3 orientations at each level, beginning at n equals 2. You see how they're all identical? They're just in different regions of space. So if you are a P orbital, you have 3 possibilities for your magnetic quantum number. They all hover around 0. So they can be a -1, a 0, or a +1. Each of these corresponds with each of these P orbitals drawn. They're not assigned to each one. They're just saying there are 3 distinct P orbitals that exist where electrons can be found. It's like 3 identical classrooms on the 2nd floor, but they're in distinct spaces. Let me try to see if this helps. If I list 3 orbitals here, let's kind of decode them. 2 means I'm at energy level 2. The azimuthal number tells me the shape. And remember, 0 means S and 1 means P. So far I know I'm at energy level 2, and I'm a P-shaped orbital. Well, at that level, there are 3 P orbitals available, right? I see them here in front of me. And so these 3 P orbitals have distinct magnetic quantum numbers, which are -1, 0, and +1. So the 2, 1, -1 corresponds with one of these pictures. 2, 1, 0 corresponds to another, and 2, 1, +1 corresponds to a third. It doesn't matter which of these goes with which picture. All we want to know is that these are identical to each other because they're the same size and shape, and the only distinction is their orientation in space. So these 3 orbitals are separate, but they are called degenerate orbitals because they have equal energy to one another. Electrons will fill them up equally because they are very identical to one another. Okay, if we are an L equals 2, meaning our azimuthal number is 2, that means we're a D-shaped orbital. You can see there are 5 D orbitals. We said they mostly have a clover-like shape. This one kind of looks more like a pacifier. But here are your 5 D orbitals. And we know they're clover shaped. There's 5 at each level, and they begin at n equals 3. Okay, so if there's 5 options, that means there's 5 orientations, which means there's going to be 5 magnetic quantum numbers assigned. They always hover around 0, so -2, -1, 0, +1, and +2. Each of those numbers corresponds with one of these pictures. It doesn't matter which is which, it's just telling me that they are all different in space. So see if this set is clear. They all have the same principal quantum number, meaning they're all of these orbitals listed here at n equals 3. They're 3 steps away from the nucleus. They all have an azimuthal number of 2. Remember, 0 means your S, 1 means your P, and 2 means you are D. So all of these right now are at the energy level 3, and they all have a D shape. Okay? The only difference is this magnetic quantum number here, which just distinguishes that they are in different regions of space. I don't care which one is in which space. I just want to know that because of these numbers, they are 5 different distinct orbitals. These, once again, are called degenerate because they have the same energy level and the same shape. So they're equal to each other. They're just different areas, okay? And we need to know what are the possible magnetic quantum numbers for each of the different types of orbitals. So if you know that there's 5 possible ones, they have to range around 0. So they're going to go down to -2 and all the way up to +2. So lastly, if we look at the F shape, well, we know that there are 7 F orbitals at each level, beginning at n equals 4. I don't even draw them here because they have various shapes. But we want to know there's 7 of them. They begin at n equals 4. So think there has to be 7 different magnetic quantum numbers ranging around 0, from -3 all the way to +3, because it's showing there are 7 different orbitals. So this table is just trying to sum up what we've talked about so far, where if at n equals 1, you can see that there's only an s orbital. At n equals 2, there are s and p orbitals. At n equals 3, there's sp and d orbitals. At n equals 4, there's all 4 sp, d, and f available. And here are those magnetic quantum numbers that are showing the different orientations. Like S will always be 0. It only has 1 orientation. P will always have 3 orientations, -1, 0, and +1. A D will always have 5 orientations, -2 to +2. And the Fs will always have 7 possible orientations, -3 all the way to 3. Those are the 3 quantum numbers that describe an orbital. There is a 4th number that's used in these quantum numbers, but it's more so defining something about the electron that's found there, not about the space. So what we know is that in each of these orbitals, each of these areas, you can have up to 2 electrons, but they have to have opposite spins. That's what the Pauli exclusion principle tells us. This is a really important principle. So each orbital, like 1, 2p orbital, 1, 3d orbital, one orbital can hold up to 2 electrons. It can be empty. It can have 1 or it can have 2. So the 4th quantum number that's used sometimes is called the spin quantum number, m(s). And all it's saying is that there's 1 electron that's going to be spinning +1/2 and one that's spinning -1/2, which really just says one of them is going clockwise, one of them is going counterclockwise. So if we decode this, 2, 1, 0, +1/2, okay, n equals 2, that's 2 steps from the nucleus. L is 1, that means I'm a p orbital, because that gives me my shape. 0 gives me my orientation, it's just saying I'm one of the p orbitals available. And the +1/2 says I am an electron that is found in that orbital that I just described, and I am spinning clockwise, which means there could be another electron that is 2, 1, 0, and -1/2. There will never be another electron that is 2, 1, 0, +1/2 because it would have the same orbital and spin. Remember, if there's 2 electrons in the same orbital, so if all of these numbers are the same, then one of them is going to be +1/2 and one's going to be -1/2. It doesn't matter what it means except that it's indicating one electron is going one direction and one electron is going the other.